Okay, this video is the first of two videos dealing with calculations of pH. So the first one we'll deal with acids. The next video deals with bases. They're much the same in terms of the process, so it shouldn't be too difficult to pick up on this. First question, calculate the pH of a 2.055 times 10 to the minus 5 mole per liter solution of perchloric acid, a strong acid. So when you see that term strong acid, you should realize this should be pretty straightforward because it's a strong acid. Strong acids dissociate fully. So 100% dissociation. And when they dissociate by 100%, it makes for a pretty straightforward calculation. So here's our dissociation expression. Perchloric acid dissociating 100% into H plus ion plus ClO4 minus anion. If we know the concentration, which we do, of the acid, by extension, we then know the concentration of the anion, or the ion, both ions. And for us, we're only interested in the hydrogen ion. And so, we're only interested in the hydrogen ion. And so there's the concentration of the hydrogen ion. So once we have concentration, we just plug it into our pH calculation, and we get a pH for this strong acid equal to 4.687. So pH 4.687, pretty low pH, should be it's acidic, and that kind of makes sense. But pHs of weak acid or strong acids are really straightforward because they dissociate fully. That's what this single direction arrow implies. It's not quite so straightforward with a weak acid. It's not that difficult, but it's not quite as straightforward because what we have is an equilibrium situation. So this is hypochlorous acid, same concentration, but it's a weak acid as it mentions here, and weak acids have Ka values. So the first thing we're going to do here is write our equilibrium dissociation. So here's our acid HClO in water yielding hydronium ion. Remember, that's the same as H plus, and this hypochlorite ion, ClO minus aqueous. So there's our equilibrium, or our equilibrium dissociation, and we want to create a nice table because we need equilibrium concentrations before we can plug into a Ka expression. So we do know the initial concentration of our acid, and we do know the initial concentration of our products. They're 0. This is going to change by a factor of x, yielding 2.055 times 10 to the minus 5 minus x at equilibrium. And as we know now, these products vary by a factor related to the change in the acid, so they both increase by a factor of x. So there are our equilibrium concentrations. And so we're just about ready to go. Now, before you go any further, you want to look at this Ka, which is pretty small, and the initial concentration, and see if you can apply the 100 rule. 2.055 times 10 to the minus 5 divided by 2.9 times 10 to the minus 8 is greater than 100. I think it's about 780. I forget exactly what, but it's definitely greater than 100, which means we can make the assumption. So make the assumption, because it simplifies things. So again, write down your assumption because Ka is so small. Assume that 2.055 times 10 to the minus 5 minus x equals 2.055 times 10 to the minus 5. Now we don't have to solve a quadratic equation. So the next thing we're going to do is write our Ka expression. So Ka equals, and this comes from our equilibrium expression, so Ka equals concentration of hydronium products over reactants, hypochlorite ion divided by hypochlorous acid, HClO. And we know our equilibrium concentrations, and we've made the assumption. So Ka was given as 2.9 times 10 to the minus 8. So 2.9 times 10 to the minus 8 equals x times x divided by 2.055 times 10 to the minus 5. So x squared equals 5.96 times 10 to the minus 13. And x equals 7.72 times 10 to the minus 7, which happens to equal the hydronium ion concentration. Remember, x does represent hydronium ion concentration. So now we just plug into pH. Equation, and we get a pH of 6.112. So 6.112 for the pH of the same concentration of a weak acid. And again, hopefully that makes sense. So that is less than our pH of 4.687 for the strong acid with the same concentration. And that should make sense because the strong acid dissociates fully. The strong acid has more hydrogen ion in solution, so it will have a lower pH. So calculations of pH involving strong and weak acids, you should endeavor to practice those calculations. And that concludes this video.